Welcome. This is the Stanford FinTech Meetup. We are being graciously funded by the Stacks Foundation. Many thanks to them. And we're going to go over a time-locked Clarity smart contract that is in a book from Stacks called Clarity of Mind. Keep in touch. So after this workshop, you certainly may reach out and join one of our meetups. There's also lots of good things to do. Send me email, whatever you would like. We'd love to hear from you. The style of today's discussion is hands-on. I hope you pull up a keyboard and try to follow along with what we're doing. We are really focused on low or no IDE help. IDEs are great. There's a great number of cool things that we can do with Clarity and the Stacks Foundation. But we're going to kind of straightforward focus on Clarity itself. There's a repo associated with this discussion that can be found right there. We're assuming you're familiar with basics of blockchains, for example, block height. We assume you're somewhat new to Clarity, and we're going to jump in from there, although maybe you've seen a little bit of Clarity, I'm hoping. Our goal here is to get a better understanding of Clarity, and specifically a time-locked contract. Again, this is from this particular book with that web link. The repo structure is, we have some code, a few contracts, some PDFs, including these slides. Should be straightforward. If you want to do a PR in there, go right ahead. I'll probably take whatever you want to put in there. And here's our agenda. We're going to start out discussing motivation. Why would we want a time-locked contract, and what time will we base this on? We're going to hit some Clarity foundations. I assume we know probably a little bit about Clarity, but we'll jump into a few more things as we go, and then we'll actually build the time-locked contract. The motivation of our discussion is smart contracts and Clarity in particular, but to get there, we want to talk about the context. Okay, and we'll talk about smart contracts, we'll talk about block height, and we'll look at some requirements for this time-locked contract. So, smart contracts. So traditional contracts, going back many thousands of years probably, should be fair and transparent. They should have measurable terms and conditions that have clear outputs, schedules. They should be legally enforceable. They should be immutable once the contract is signed and executed. Can't change it. And of course, they're fundamentally to accomplish a goal. So this is traditional contracts, often in paper. Smart contracts, work with proof of work of blockchain, or for proof of work blockchains, are fair and transparent. There's no trusted third party. Terms and conditions, these should be measurable, inputs and outputs, schedules, distributed consensus. That is to say, a bunch of strangers who will be able to validate and verify by majority vote that the contract is valid or these terms and conditions have been met. It should be immutable. Once the contract is set in place, can't change it unless it specifically specifies that. And it's programmatically or eventually, if push comes to shove, legally enforceable, and it accomplishes a goal. Often these goals are executed through cryptocurrency or tokens. So we have this in proof of work blockchains. Very nice. The foundations from blockchains, of course, we all know blockchains are immutable. This is a necessary piece for contracts. Programs, we must be very careful with our programming for smart contracts because of that immutability. There's been famous cases of smart contracts losing resources for good and things like that. Distributed consensus, we have to agree on terms and conditions of a contract and when they're met. So we, again, a bunch of strangers should be able to review that. That's not too different from a regular contract. In the traditional contract, you end up in a trial by a jury. These are, a bunch of strangers, almost by desire and need, and they would agree that the terms and conditions have or haven't been met. Finally, in our case, we're going to transfer tokens or cryptocurrency, and our example today we'll talk about simple cryptocurrency, that is to say Stacks coins. Smart contracts are digital contracts, and they're well beyond digital signatures, although digital signatures can play a role. They're on a blockchain. There's the consensus evaluation automatically done. Originally, these were proposed by Nick Szabó, and this also, of course, goes back to Satoshi Nakamoto and Bitcoin itself. The new perspectives we have with digital smart contracts is a contract is a program. It's executed on a network of machines. Questions of validity and verification can be done by cleverly designing the contract language, that is to say Clarity or whatever you would like. And traditionally, the laws are built and contracts are built based on statutes, and these are the written laws. Regulations tell you how to apply these laws and give some examples, perhaps some edge cases. And case law looks at the validity and verification of the terms and conditions, and sometimes even the phrases in statutes and regulations. So some of these pieces really boil down to having a programming language or a smart contract language that is validatable. Okay. So this is where we're getting some of our examples here from this particular link. And we want to mention block height because we're going to use this in this smart contract. So money has a purpose, and the key piece to it is it's a medium of exchange, unit of account, store of value. Some people look at Bitcoin's blockchain and say, well, that's really a unit of account and a store of value. It doesn't quite live up to a medium of exchange because the expected amount of time between two new blocks is about 10 minutes, and you may want to have a handful of blocks there to actually validate some transactions you make, and so that's not as easily a medium of exchange, except for maybe things that are slowly exchanged and carefully exchanged. So this has given desire to build level 2 networks or chains on top of Bitcoin that are more effective for a medium of exchange. In particular, we'll look at the Stacks chain up here. On top, the bottom blockchain could be the Bitcoin blockchain, and above it is the Stacks chain, which may have a new block maybe every 5 seconds or so, or more often. And that blockchain also will have a currency called Stacks, which will be tied into Bitcoin itself, and it will have its own economic force to keep itself going at a much higher speed, so we can have a good medium of exchange and a good way to have smart contracts. So Stacks is as a level 2 on the Bitcoin blockchain, where the Bitcoin blockchain really acts as a settlement layer. This allows as payment or exchange of tokens for smart contracts, and STX is valued based on Bitcoin, and it's done through proof of transfer, or POX. Okay, so some of the requirements for the smart contract we're going to look at today are as follows. Now, here's where you can find them also, and alternatively, I rewrote them here. Any user can deploy the contract. So this will be a piece of code. You can pull it down and run it. Okay. You must specify a beneficiary, that is to say an address in the Stacks chain or a principal, a block height for when this money will become, or when these Stacks tokens or Stacks money will be available. Anybody can send Stacks funds to the contract, and we'll look at just generally sending some Stacks around anyhow. The beneficiary can change their beneficiary. So if you're the beneficiary, you want to pass the resources to somebody else, you can go right ahead, as long as you are the beneficiary and you are the current person to transfer that. Okay. The 3 functions we're going to look at. The lock function, which creates a time-locked contract. You've got a beneficiary, a block height, and a Stacks amount. These are principal, unsigned ints for the block height and the Stacks amount. Unsigned ints because we're not going to have negative block heights, of course. The block height is nothing more than the number of blocks that have already occurred, and the block height is the actual index of a current block. The Stacks amount is also an unsigned int. We're not going to allow people to transfer negative amounts of resources. A claim is a transfer of the Stacks to the TX sender, which is the beneficiary, one and the same. And it can only be done when the block height has been reached, the block height that was specified in the lock function. And of course, bestow allows the beneficiary, as long as they're the TX sender, to change the beneficiary of the wallet or of the contract itself. So some foundations of Clarity. Clarity is a real powerful tool, but as much of what all of us do, we all build on the shoulders of giants. If you look back at any technology today, or any advancements, in my assessment, that we've had as a society or as a world, this is built on very sophisticated ideas that have been generated and enhanced over long periods of time. So we'll glimpse at the history, just to kind of take a glancing view of it. We'll mention some paradigms in engineering and applied science, and we'll drop into some examples. So part of history, the Church-Turing thesis is the statement that the notion of computation of a stored program computer is captured by the lambda calculus, the Turing machine, the post-correspondence problem, or recursive function theories. So all of these theories were put forth starting in the early 1930s and shown to be equivalent. That is, Alonzo Church's lambda calculus was originally designed to capture the notion of computation from a stored program computer. Before stored program computers existed, likewise, Alan Turing built something we call the Turing machine that also captures our notion of a stored program computer. Likewise, Emil Post's correspondence problem Hartley-Rogers recursive functions theory, and these are all equivalent. They all emulate what we have today in our computer desktops or in our smartwatches, in our phones, all these other things, these computationally equivalent devices. So this goes way back, but as an extra boost, Church's lambda calculus turns out to be a foundation of a programming language called Lisp. John McCarthy is famous also for implementing an early version of Lisp in the 1950s. Two of my favorite flavors of Lisp are Common Lisp, although that's kind of big, and Scheme Lisp, which is small, sleek, and kind of elegant. But these are great examples of Lisp still to some degree in use. Common Lisp is much more so than Scheme, and there's Clojure, there's a bunch of other Lisps out there that are very nice and useful. Clarity, as you know, is built on a Lisp-like language, or is a Lisp-like language. So the important piece here, why do we concern ourselves with this? Because engineering applied science has many paradigms, and these paradigms are tools in our tool chest to build great things. Okay, so for example, in terms of programming languages, we have object-oriented paradigm, we have a data-oriented paradigm, functional, procedural, imperative, declarative. It goes on and on and on, and this has led to many different ideas, and actually this enables us to solve certain classes of problems more effectively in many cases. That is to say, if you have a certain type of problem, one of these different ones of these paradigms may actually allow us to solve that problem better and more efficiently, more effectively, and quicker. This has led to some differences in thinking. So, for example, in terms of clarity, we have the functional paradigm we're taking. We're picking that up from the lambda calculus, or actually more recently from Lisp-like languages. Solidity is an object-oriented language. Largely, and it picks up off on the object-oriented languages. And this is just how many of these language paradigms work, and this is a tool that you may choose from your tool chest to solve your problems, the challenges that you get hit with. The essence of a contract: what should a smart contract be? What should it not be? How should it run? And a very important thing is the validity of a smart contract. We know from years of studying logic and some of the great results in logic that we actually have these issues of validity and provability in logic, and because of Clarity's choices of design, that functional chunk that it works with is actually decidable. That is to say, any statement in Clarity, we can prove or disprove what outcomes it will produce. Some simple examples of smart contracts. So first thing is, I'm going to presume you're a little bit familiar with Clarity and Clarinet, the system that runs it on the desktop. So there's a Windows installer. You can install it on Windows, WinGet install Clarinet. You can install it on Mac OS with Brew install Clarinet. Likewise, you can install it in a Linux box. And I'm presuming you already have Clarity, or at least you'll install it here. It should be fairly straightforward to install it. Once it's installed, then you can create new projects. You can go into them and you even create new contracts, and then you can get the Clarity console through the Clarinet console to interact with your Clarity contracts. So like Lisp, Clarity, which is a flavor of Lisp, is a prefix-oriented language. That is to say, the operator is put first after a set of parentheses, and all the operands follow that. And these different operands may be recursively evaluated. You'll see in line 2 of the Clarity example, the system itself will pick off the plus operator right in the front and say, hey, we're going to do some addition. It gets the 1, then adds that to the result of the addition of the 2 and 3. So we have a 5 there that replaces that expression, and then 4 divided by 2 is going to be 2. So we get a 7 or an 8 in there, and so it evaluates that. We have a power function which generates exponents. We can intermix all these in different ways. This is different from the usual infix notation you see in many programming languages, and also when people just write stuff out. That is to say, put the operator between things. Here we're putting the operator right up front to be clear about it. And it's a nice. The prefix operators, I think, are a very nice idea. There's of course postfix operators as well, and stack languages, and there's all sorts of other things. So there's a reference here. Here's a couple of simple functions, straight out of the Clarity, references. The first one is simply hello. Notice it returns a OK surrounded on the hello, and that the idea there is just to give us a thumbs up or thumbs down whether something worked. When we have an error, we can also return an error wrapped around that, and that can unwind some things that were already computed, which is something for another time. So here, the second line here is hello, name, and notice the ASCII string here is limited to 10 characters. That is important because Clarity is very careful about provability and validity, so we don't want to have an overflow. Some of the overflows in various languages have caused all sorts of challenges in the validity of the statements of the language. So I'm just going to pull up here, and we'll make this a little bit bigger. And let's go here. And we'll go into our console here, and we actually have these, but I'm going to go back and I'm going to load. Let's see if I can read in my function here, and then so this function, let's pull up exactly what this function is. So these are my functions we were just looking at. One simply says hello, and then hello again actually says hello, and it has a name, which is a ASCII character string up to 10 characters. Okay, and that actually gives a more precise statement of hello. So we're going to execute the first one. Okay, I have to specify the particular address or the principal that this contract lives at, so I can actually run it. Okay, in this case, I have a contract that I saved out, which are just the files we just looked at, these functions we just looked at. Now I want to say hello, and I have no arguments, so this will just say hello, and then I can say hello again. Oops, and I can say hello, Alan. And of course, this second function here, which we just looked at a minute ago, gives us this more specific hello. But now I can turn this around and say hello, Alan Turing, and we're going to get a problem because Alan Turing with that space is going to be 11 characters, so we're going to get an error here. And this is what it tells us, that hey, we found a string that's 1 extra character or 11 characters long, and this is a problem. So Clarity was designed very carefully to make it things provable in a good sense, which is very, very important and very useful. So we can go from there, and as we just saw what happens here, which is nice, we can also pass in values. So here I just want to talk about briefly, just a review for, public and private powers and things of that nature in here. So we can go in here, and I could even define it in here if that makes some sense. So we can say define public, I'll say private cube, I'll make this a private function, and I'll have x int. So we have a regular integer coming in as our x, and then because this is a private function, I don't have to wrap it with an OK or an error. I'll simply say x23. That wrapping it with an error or an OK actually helps us out, gives us more security. And then, of course, I'm going to do something interesting here. I'm going to say define. I hope you find all this interesting, but define public 10th power x. Okay, oops. Sorry, I need to say x int. And what I'm going to do inside the 10th power here is I'm going to go multiply x times cube of cube. Now, cube of cube is, of course, the 9th power. And so cube of x in here. So let's see what we have here. Cube of x. I think I need maybe missing parentheses here. I hope that's the right number. And I have to return, in fact, an OK here, or an error. And so I'll put an OK there. I hope I got the right number of parens here, but we'll find out. And then I'm going to reload this, and then I'm going to run the 10th power. There's an important thing to note here. I'm computing the cube of the cube. Okay, so cube is calling itself, but not in a recursive notion. So let's go back here, and I'm going to reload this function here. And let's try, first of all, if we try to run this, the contract here, simply the cube contract, is going to complain. And the reason it's going to complain about the cube contract because that is a private contract. So let's go here, say cube of 3. It's going to complain. We're going to get a nice complaint here because you'll notice as we set this up, this is a private, so it's going to say, hey, nobody else can access my private cube contract. Okay. However, if I want to do a 10th, okay, let's compute 2 to the 10th power. So 2 to the 10th power is 1024. Not too bad. Oops, we got an error here. Let's see what we have here. TENTH. Contract has no public function 10th. Did I make a error here? Define public TENTH. I misspell something. Let's see what I have here. Doesn't like that, so I have to find out what is going on there. So we have cube times OK define. And let's go read this back in. Actually, I'm going to drop out, run back into the console. Let's go read this guy here. And I think that it should be fine. 10th. There we are, 1024. I must have had a typo somewhere. So we can compute the 2 to the 10th power, which is great. And then we, of course, going to go power 3 to the 10th. We'll see what this is. This is that number here. And we can try our contract here. I'm going to 3 to see if these two things match. And in fact, they do. We're in good shape. So we have a nice 10th power contract. Now, of course, we can also use this simple function here, but we want to understand better how we can interact with these contracts. And the interesting point here is a contract can call itself, but not in a recursive sense, not based on conditions that may vary. So in hitting a base case, then hitting a recursive case. So we can call ourselves, but not with full generality, which is quite interesting. And so this is going to lead us to another interesting idea here, which I want to always jump into some classics. So here's a classic factorial function, which of course is recursive. This is the typical way we present this in mathematics. And right on the bottom, we have a recursive factorial function from Scheme Lisp, one of my close friends. And down here, of course, this recursive method we can't really execute in Clarity because it's illegal. So in fact, we will go here. Recursion is illegal in Clarity because recursion adds the risk that we cannot have a fully validatable or fully decidable language. Also, looping is restricted to being map, filter, or fold. So these three functions are the only way we can really loop. So how are we going to implement these factorials? So here's some examples. So what we're going to do is we're going to use fold, and let's take a peek. Okay, useful thing to look at. Right here, let's see if I have, here we go. So you're right on the screen, you can see here's something we'll look at in a minute, but here is a list itself, 1 through 4, containing this, and I defined it as a constant, and then we're going to have factorial of 4, which takes the fold function. Fold takes this operator, applies it to this and the first element in here, and just keeps recursively applying that through that list until we get done. And so this will actually multiply 1 times 1 times 2 times 3 times 4, which will give us 4 factorial. So let's take a peek at that. Okay, we want to do that. And this is in, I think, contract C2. So I want to go in here, and I'm going to read, so I'm going to read contract C2 in. Okay, and then I want to run this factorial function. So I'm going to say contract call, let's give the whole contract name. So it gave us this. This is a principal or the address in the Clarity, in the test chain that we have on this computer that I'm using here. And so here is the actual contract. I want to use this to call fact4. So I'm just going to say fact4, and this should give us 4 times 3 times 2 times 1. So 4 times 3 is 12 times 2 is 24. Okay, so that in fact works, which is nice. And then we have another little snippet of code I just want to mention here. We have this notion of stacks transfer. So if we take a peek here, when we booted up our Clarity, we'll notice that we have all of these different addresses in the stacks chain, or these principals have a value already associated with them. These are in hundreds of billions of a stack, of a stacks coin. So I can go, for example, and transfer some resources from here, okay, from this address. Okay, so I can go stx transfer, I'll say U99999. I want to transfer it, actually I should probably transfer it from myself into that one. So I will transfer it from tx sender to this particular place in here. Okay, oops, so let's see what I did wrong here. TX sender. Okay, so we'll go from there. M is M. Something wrong with M. I don't know. My mistake. So I guess it's GM. So I have to take a look at the particular principles I have now, because I have uploaded a different contract. So I'm going to get. Let's see. We'll get all of our. Actually, yeah, this will be, I'm going to go here and just use my help function, and I'll simply say get assets maps. Okay, so here we are. So now I want to actually transfer, tx sender will be this. I'm going to transfer some 300 U stacks to there. So I'm going to go back and let's see. So I think I was transferring it to myself actually, which is not a great idea. So here I want to do this, okay, and so now if I, and that says it succeeded, so when I get my assets maps, you'll see I pulled out 999 and I put it in over here. So we can do a transfer to the different principals on the stacks chain. Now on to building the time-locked contract. So we'll talk a little bit more about the background, a teeny bit about the contract model, and we'll just jump into the example. So here's where our source is. We mentioned Clarity is decidable. That is, any expression you give us in Clarity, we can prove what it will return and what it will do. Clarity guards against overflows and underflows. Because Clarity is a functional language, not object-oriented language, it has composition rather than inheritance, which can be good. Inheritance has some features such as polymorphisms, etc., that can be challenging. So in general, when we boot up Clarinet on our desktop, we end up with a contract identifier, as you see right here. And a contract identifier is a stacks address dot the contract name, and of course the public functions are listed. This means anybody can execute these functions. They may or may not be able to use them. These functions can actually ask, is this, who is executing this function? Is this the right person or not? Or right contract, I should say, or right principal. Then below here, we have just simple addresses on the test network. And more precisely, here's a principal address right here. The leading ST indicates it's a test network. The second principal here is actually a contract principal of the first principal. That is, we can have a bunch of contracts associated with a particular address in the stacks chain. And each of these contracts can have values of its own, which makes a lot of sense for smart contracts. Each smart contract can actually have a certain amount of stacks coins with it in the stacks chain. So here is a simple get balance and add to method. The function add to takes two arguments. It takes an amount, which is an unsigned integer, and it takes a principal recipient. And as long as that amount that's being transferred is even, then in fact the transfer will occur. Otherwise, we report an error. Okay, so let's take a peek here at how to do that. So I'm going to go to, we'll do this, and in fact we have this add to method here. So what we're going to do is going to go contract call dot, this is the time locked contract, so I'm just going to get time locked. In our time locked wallet we have these public functions, which includes the add to, and I'll go paste this guy right here, and then I'll simply say add dash 2, let's give it a U990, and right now we are in this particular contract. Then when we start, or this particular address, we are going to our principal we're associated with. We're going to send this resource to here, and so let's do that clearly like that. And we have an OK true, but I'll go to get asset maps, and you can see we transferred 990 to this contract right here, which is the same as this one up here, and we pulled it from here, and this of course is nothing more than the TX sender, which is our current contract that we're sending stuff from. So now what we want to do is, so we can do this, and this is great stuff, and we can also, of course, we can make it fail too, so we might as well do that as well. What I mean by fail is we might say, okay, I want to send an odd value to this contract ending in PD5. So this is going to give us an error, and the error in this case just indicates that we've not done what we hope to do, because we chose to try to send an odd value in, and you'll notice this is equal mod amount, the amount we're sending, divided by the unitary, or should I say the unsigned 2. If it doesn't equal 0, then we're gonna go to the error on the bottom. Okay, so we have that, and as long as we're there, let's take a look at the other things good to know. So the first thing is we have constants we can define in Clarity. For example, the contract owner can be assigned to be the TX sender, okay, which is our global variable describing what we logged in as. We might also have a map of recipients, and these recipients are simply associative pairs of principals and amounts. And these, in the simplest terms, here are the principals, and here's the amounts that the principals would have, or this we might lock into this contract. In that case, it would be principal contract principals. Okay, so this is directly from the book itself, the Clarity of Mind book. These are some. First thing we do is we set up the TX sender, then we set up some errors. We start with the beneficiary being empty and the unlock height being 0. So we say, okay, here's some basic things to start with. The unlock height, again, is the block height, which is the index of the current block in the stacks chain. So here we have the lock function, and it has 3 formal parameters: new beneficiary, unlock at, that is, they say what height this contract will allow money to be transferred, and the amount that is going to be transferred. And so we have a bunch of asserts here to set things up to make sure things look coherent, which is a very common thing, especially if we're going to try to prove something to be true. So the first thing we do is make sure the TX sender is a contract owner. Recall we set that in one of our constants previously. Next thing we do is we make sure that the beneficiary is empty to start out with, because we have a new beneficiary right you see at the top of the screen here. Then we make sure the unlock height is higher than the current block height. Then finally we check to make sure the amount we're transferring is bigger than the unsigned 0 integer. Finally, we try to do the transfer, okay, to make sure there's enough resource in TX sender. We're going to take an amount from TX sender to the TX sender contract, okay, which the contract is actually what we're creating right here. All right, and then we of course set up a beneficiary, we set up the unlock height, and we only want to do those things if everything else is go, and then the OK true is simply what the begin expression will be returning. We can bestow, if we are a TX sender, we can bestow, and the beneficiary, we can bestow the rights to take this contract and actually get the money from it, the resources from it, right here. We first want to make sure the TX sender is the beneficiary. Then we're going to reassign the beneficiary to the new beneficiary, and return true. Finally, the claim. So we've set this resource up. We've set a principal contract with some stacks coins in it, and we want to check now to claim it, or we want to actually claim it. So the first thing we do is we make sure the sender is the beneficiary. We're going to, so that they can actually get the resource. Then we want to make sure the block height, okay, the second assert here, make sure the block height is at least as big as the block height that was specified, okay, to be the unlock height, that is the specified, so we can only get this money once we've had so many blocks, okay. And then finally we do the transfer, and we do it as a contract because we want to send it to the contract here, not just the address. Okay, so we do all that. So this is really good. So let's take this for a test drive. So we're going to go contract call. I'm going to say time wallet. Then we are going to say, we're going to go lock. That's the function we're calling. We're going to say, I think it's U999. We'll transfer this much. Oh, sorry, we want to transfer to. So we want to pick a recipient. I'm going to pick this recipient right here. Just want to make sure this is what we have. We have, okay, the new beneficiary, unlock, and the amount. Okay, so here is our new beneficiary, and then we have the unlock height. I'll make it 10, and then the amount, I'm going to make it something nice and big. And then we'll put that there, okay, and we get a OK true returned. So now we might want to take a peek here at our get. Okay, here's our asset maps. Here's our time locked wallet, which now actually is, okay, this is the same here as TX sender. So if we go TX sender, you'll see this is our current TX sender. This is the global variable. This is who we're coming from. In there we have a wallet that is holding this amount of resource. Similarly, I'm going to go help for a second here, and we'll say what particular block height do we have right now. So we're going to get the block height. Right now we're going to be a block height 1. Yes, the stacks chain moves far faster than we've been moving, but this is just to understand blocks better. We're in a simple test mode here. And so we get the block height. So right now, if we try to claim this resource, so I'm going to go back here and say, okay, great, I want to actually just claim this money for myself, and that's all fabulous, and that's everything else. So let's try to make this claim here. So the time lock contract, we might want to do a claim here, and we get an error 104 because we're not the right person to do the claim. Let's take a peek back at who is the right person, just so we can go back here. So this is PD5. So we're going to have to actually change ourselves to be PD5 to do the claim. So there's two issues here. And then also we have to make sure the block height is correct. So what I'm going to do here is I'm going to set, let's see, set, what are we going to do here? Set epoch. Well, actually, let's set TX sender. Okay, so I'm going to set TX sender to be this particular contract address, because I want to get that money to myself. So now the TX sender is that. So now I can actually claim that, except I may have to make sure we're at the right block height, and we are still not at the right block height yet. But let's try to get this anyway and see what we get as an error. So I'm going to go back to do contract call claim. Okay, and then we do a claim here, and oops, oh, time block wallet. So the claim, we actually have to specify the particular contract we're coming from, your unresolved contract. Okay, so this is not the right contract, but so I'm going to specify the contract. We're actually going to pull this whole thing out right here, and what we'll do is we will now, I'm going to pop that in because I'm running from TX sender as a different address. I have to also put in a little quote in here. So now I'm going to try to run the claim. It's going to fail again. Okay, this is a little different failure than before. Before we got 104, now we got 105. We are not at the right block height, so we're going to set the block height so now we can actually transfer it to ourselves. But just before we do that, let's peek at the values again. So I'm going to get asset maps. So we still have this contract principal that contains this. This is the one that now should own, or effectively the beneficiary of this contract should be this guy, and this is our current TX sender. We'll verify that again. TX. Okay, that's correct. It's YPD5 right at the end here. So that looks good. So now what we want to do is we want to set. Actually, let me go help. We get it precisely. So we're going to set advanced chain tip. So we're going to add 10 to the chain tip so that we're in fact going to be within the right time. So now we can say get block. So we had 11, so we should be good. That this contract should be transferable now. So now what we want to do here is, let's go back here. So this is the owner of this is the actual contract principal right here. We're running this, but we're running this as the TX sender, but that's okay because the beneficiary was set to us too. So now we should get the claim. So it says yes, and then we can go get assets, get assets maps. So notice the block itself here, the principal contract here has 0 in it now, but this is the YPD5. Now we've just added that value into here. Okay, so we added the value in there. Let's see what the value was. I'll make sure that makes some sense. Oh yeah, it's 9999. And oops, previously we had added 990 in there, so it's a little bit more. So we'd have 990 to 999. So we can even do a plus 1999. See what we get here. So we get 10989, which is 1009, which is exactly this. So it actually worked out. And that's all we have. I want to thank everybody, and hope to see you again, maybe at the Stanford Tech Meetups, or the Stanford FinTech Meetup.